for the introduction, the invitation to speak here. So let me get sort of started with explaining one part of the title, which is the flat surface part. So what is a flat surface? We'll consider, for the purposes of this talk, we'll consider a finite family of polygons, which are subsets of R2, or you can view them as subsets of the complex plane. And you'll form a flat surface X out of them by gluing sides or parallel sides or anti-parallel sides of equal lengths using either translations or reflections, depending on whether the sides are parallel or anti-parallel. So I've drawn two examples over here. One is this octagon. So in this case, I've simply glued together opposite sides of this octagon, and you form this genus 2 surface over here. Another case which uses anti-parallel sides is the so-called pillowcase. So here you have two unit scores, and you glue one of their sides together like this. You glue these two vertical sides again by a parallel translation, and then you glue these pairs of horizontal sides by anti-parallel translations, which gives you something that looks like a pillowcase. Okay, so these are two examples of flat surfaces. Another way of thinking about these objects are through meromorphic quadratic differentials. So a quadratic differential is simply a tensor of differentials, a square tensor of two differentials, which is locally in the form f of z, dz tensor dz, where f is some meromorphic functions whose poles are all at most simple, so no double poles or higher. So we can get a quadratic differential from one of these flat surfaces by taking the one form dz, the quadratic differential dz tensor dz on each polygon, and simply gluing them together by these translations or reflections. The reason you want to have dz tensor dz, namely the reason you want to have a quadratic differential, is to make sure that the sign doesn't mess you up in the reflection, right? The reflection will flip the sign of dz, but if I have dz tensor dz, that sign is reverted back to what it was, to being 1, and now the gluing makes sense once again. Okay, so this procedure I mentioned can be reversed in a sense. So I will not really explain how, but maybe you can take my word for it, that given any sort of surface and a quadratic differential in, I can reconstruct a family of polygons that you can obtain to glue the surface back together. Okay, so the question that I'm interested in this talk is, how does a typical or a random flat surface look? Okay, so I owe you two things here. One is what I mean by random, and second, what do I mean by look? So I'll try to answer these questions in the coming slides.
Is there a symmetry condition satisfied here by the quadratic differentials you get from this construction?
Sorry?
There seems like there's a symmetry condition, right? Like you can swap two components of the tensor. Or maybe that's hidden by the word such. I mean, my question is this, can you get it?
Yeah, such, it's hidden by the word such, yeah.
That's a flat singularity.
Sorry? Flat with singularity, it has conical singularity, it has compounds, you're right, yeah. Okay, so I want to discretize this problem so I can pick. I want to make a finite set of flat surfaces that I can pick at random. So let me explain how to do that. So we'll restrict our attention to square tile surfaces, which sort of you can view as discretizations of flat surfaces. So these are connected flat surfaces obtained by just gluing unit squares together. So I have a finite collection of 1/2 by 1/2 squares, and then I'll glue pairs of vertical or horizontal sides once again by reflections or rotations. I gave you the simple example of the pillowcase on the previous slide, and as Peter just mentioned, these surfaces will have what are known as conical singularities, which are points whose total angle is not pi. Okay, so these are also defined on general flat surfaces, not just square flat surfaces. So if I go back a slide, I know that I've over here all of these. If I didn't make any mistake, all of these 8 vertices in this picture are identified to a single point. So this single point will have angle 720 degrees or 4 pi, or 4 pi, which is more than what you expect, namely 2 pi. So you'll have this. So this surface is going to be its flat surface with one conical singularity whose total angle is 4 pi. In this case, what you'll see is that you have 4 conical singularities, each of angle pi. So you kind of half the angle by this anti-parallel gluing procedure. Okay, so the idea basically is that any conical singularity will either have total angle pi or total angle 2 pi times n plus 1 for some integer n that's at least 1. And these conical singularities, in terms of what it means in terms of the quadratic differential, is that these are going to either be simple poles or zeros of the quadratic differential, namely a conical singularity of total angle pi is going to be a pole, and a conical singularity of total angle 2 pi times n plus 1 is going to be a zero order n. Okay, so I can now try to say what I mean by random. So we'll let Sn of g comma n be the set of all square-tiled surfaces with the following three properties. Okay, so first I want to have n 4n square. I mean, 4 is just, 4n, because each square, I remind you, was 1/2 by, this is just normalization. Each square was 1/2 by 1/2. So this guarantees that the total area is n. Genus G, and it has n simple poles, okay, which you can, again, the total number of conical singularities with total angle pi is n. So again, so for n large, you can sort of view Sn of Gn as discretizing the set of flat surfaces of genus G and n simple poles. And sort of the questions you can ask are twofold. The first question, the question I had on the previous slide was, what does a random surface look like? But for those who study statistical mechanics, before you ask what does a random thing look like, you want to be able to compute the so-called partition function, or just the number of things, the number of objects in my class. So the first question is simply, how big is Sn? How many square-tiled surfaces are there in this SNGN? And the second is, how does a uniformly random square-tiled surface in this thing look? Okay, and I still owe you a definition of what I mean by look, but I'll table that for the moment. Okay, and the limit regime I'll be interested in is I'll first let capital N tend to infinity. So this is like I take a surface and I'm discretizing it. So I need to first let capital N tend to infinity. And then I want to let the genus tend to infinity. So my basic goal is to understand what a large genus flat surface looks like. So to do that, I first discretize so I can actually, count these flat surfaces, and then I'll let the genus tend to infinity. Okay, so I just mentioned for those aficionados of quantum gravity and random quadrangulations, this is a fairly different scaling limit than from what one considers there. Here everything is sort of locally flat, whereas there everything is actually locally very rough. So yeah.
Sorry, I should have missed it. What is square tiled? We just have one domain.
So I remind you that a flat surface is obtained by gluing together a bunch of polygons, and in the square tiled surface, each polygon is a unit square. Yeah, so it's just I can discretize any flat surface in this way. Right. So let me first focus on the enumeration question, which is so I just want to basically count the size of this SNGN. So it's a fact that goes many years back that this for n large, so I'm taking capital N to infinity first. The size of SNGN, it scales like capital N to this exponent 6g plus 2n minus 6, which is a certain dimension of a moduli space, times some constant vol of QGN, which is the volume, which some people refer to as a volume of a moduli space. So this theorem, which goes back, I guess 40 years by this point, is that this volume is finite and positive, which is it's spelled
volume with respect to what?
Yeah, I'll sketch what I mean in a second. It's with respect to a certain Lebesgue. It's the volume of a moduli space with respect to a certain Lebesgue measure. I'll say what I mean in a moment. Yeah. So it's a theorem which goes back to Vaser and Beach back in 1982 that this volume is finite and positive. Neither end of that is particularly trivial, but the finiteness is maybe the harder point. So in attempt to answer Peter's question, I want to quickly mention what I mean by volume. So this vol QGN is the volume of the moduli space of meromorphic quadratic differentials. So what is this moduli space? It's simply the set of pairs XQ, where X is a Riemann surface and Q is a quadratic differential on it. This is known to be a non-compact Orofeld, so it can have cusps of dimension 6g plus 2n minus 6. And this dimension is exactly the same as this exponent up here, as you would expect. Namely, if you take some n-dimensional body and you count the number of lattice points inside of it, you expect to see exponential in many points. So that's sort of the reason why you have this exponential here. And volume with respect to what? So we can put coordinates on this moduli space, which is what are often known as periods. So this moduli space is parametrized by periods, which are basically the sides of the polygons you glue to form this x comma q. So these are just a bunch of vectors in R2, or I prefer to think of them as complex numbers. So particular square tiled surfaces, they have periods all in 1/2. Again, that's just the half by half squares. times z adjoint I. So these are, basically like Gaussian integer scale by 2, right? So you can view them as kind of like lattice points inside this moduli space. And now I've periodized. I put in periods. I put in these lengths. So I basically taken my moduli space and mapped it to C to the. I mapped it to some complex space. The complex space has some measure on it, and by pulling back that measure, I get a volume form on this moduli space. And this vol QGN is the volume of the moduli space with respect to the volume form.
I'm quite happy if you fix G and N and let capital N go to infinity, because there's an unknown constant there. But since you highlighted you can let G go to infinity,
yeah.
Then how do you normalize the volume form?
So
have you normalized the volume of the quotient to be 1 or not?
Well, so I'm first letting that to infinity, and then my job, as you mentioned, is to compute this vol QGN so that I know how to, so that
Right, but isn't it that unique? There's a volume form that's unique up to a scalar.
Yeah.
What's your
yeah, right. Okay.
It's only because you're going to make G go to infinity, so then I need. Maybe
okay. So right.
You're making your unit square area 1 or something.
Yeah, exactly. So yeah, you're exactly.
Okay. I mean, like when you take the base measure, usually you make the unit interval length 1.
Exactly. Yeah. So you want to make some sort of unit, in this case, unit Q, I guess, of a volume 1, right? And then there are various choices and normalizations though. Yeah. It's somehow not consistent in the literature. But yeah.
But when you give us an asymptotic when G goes to infinity, you better be normalizing each one.
Yeah,
the same way.
Yes, of course. Yes. Yeah. Okay. As I mentioned before, the analogy is that if I take the volume of some disk and I try to count the number of lattice points in it, it's going to be something. It's going to scale like my discretization, my epsilon inverse to the dimension of this disk. So that's where you have this n to the 6g plus 2n minus 6 times some constant, and that constant is this volume. Right? Okay. Now there are various formulas or algorithms to compute this volume. Which are all somewhat complicated. So I think maybe among the earliest was due to Eskin and Okunkov back in 2005, and they used basically asymptotic representation theory. They interpreted this as counting branch coverings, and they used Hurwitz theory or asymptotic Hurwitz theory to do that. Another approach goes back to Mirzakhani in 2008, who related it to volumes that appear in hyperbolic geometry. Yet another one is by Delecroix-Goujard-Zograf-Zorich in 2019 through basically relating it to ribbon graph counts. And another series of works by Chen, Muller, Zavajay, Kazarian, and Yang Zhang are by interpreting these volumes as certain intersection numbers and recursively computing those intersection numbers. So there are a number of ways in which you can compute these things. And you should not expect any of them to be trivial. And the reason you shouldn't expect any of them to be trivial is that the volumes themselves are not trivial. They're fairly complicated objects. I remember someone referred to them as irrational rational numbers, meaning that, they're rational up to various factors of pi. They're rational, but they're completely crazy. There's no real pattern. If you try to look at, say, already, if my genus is 4, I have some.
The only mystery is the rational number.
Yeah, of course, yes. Or some 7-digit number over like some 12-digit number. So all of these formulas or algorithms, or so maybe the last, have some sort of exponential complexity in the genus G, which is why you expect them to be fairly intricate. Now I want to send G to infinity. The theorem is that as G tends to infinity, this volume of vol of QGN, it converges to something totally explicit. So I have a factor of 4 per pi. I have 8/3 to the 4G plus n minus 4, and then times 2 to the low one. Okay, so that's a theorem that basically fills in this prefactor over here, which is
you need n to be. I didn't see. N could be 0.
N can be 0. So I view n as fixed. So think about it as like 5 or something like that, or 0 if you like, and then send G to infinity. Yeah. Okay.
So is it known that these coefficients are always going to be rational, or
which one? Yeah. So it's known that
from the recursion relation.
Right. So actually, all of these approaches will give you that. All of these all of these, I think like 4 approaches will tell you that it's a rational.
That follows from algebraic geometry.
Yeah, I mean, it follows from
recursion, probably, you know?
Yeah.
It certainly follows from recursion.
It will follow from the recursion. It also follows from the Hurwitz theory. It follows also, I think again, so some Mirzakhani related to volumes of hyperbolic geometry could also be computed recursively. So it follows from that too. And there are some more complicated formula in terms of these graphs. And there you also see the factors of pi. So it follows from all of them. You have this rational number times pi to a specified power, and that specified power is, okay, well, I don't remember what it is off the top of my head. But
I think there's also a Kähler argument.
Yeah.
There's a geometric argument.
There's also a geometric argument that gives it to you. Yeah. So yeah, of course, I mean, the real mysteries in these rational prefactors. Although, I mean, somewhat ironically, you can see that it's the product of them that has this simple.
Let me try to sleep quickly.
Okay. So the proof, which if I have time, I'll sketch it, but I might not have time. So.
I think you probably know how to mute people.
Okay.
He doesn't know.
So the proof will be based on analysis of these sort of ribbon graph, the third of the 4 approaches I had mentioned last time for these ribbon graphs. So this approach, basically what it does is it counts square-tiled surfaces associated with some graph gamma, sometimes called a stable graph. And it basically assigns a weight to each graph gamma, and it sums over a huge number of these graphs gamma. Now, the advantage to this approach is that this graph gamma actually is going to tell you something about the flat surface. It's going to be some geometry encapsulated in this gamma. So although I have this fairly complicated sum over all graphs, if I manage to compute this sum, I'll actually get more than just the volume. I'll be able to understand sort of the contribution of any geometric skeleton, any sort of surface coming associated with this graph gamma, which can be used to sort of fish out statistical information about random square-tiled surfaces. Before I get to that, I want to now talk about sort of the hyperbolic side of the story, which are through these multicurves. So just a definition to start with. A multicurve on some oriented surface X is a formal sum gamma of a sum of mi times gamma I. So these mi's are just positive integers, and these little gamma i's are simple, by which I mean non-self-intersecting geodesics on X, which are not pairwise asymptotic. Okay, so I'll say that 2 multicurves of the same topological type if they coincide up to an action of the mapping class group. So another way of thinking about this is that if I cut my surface, I have some multicurve, which is just some collection of simple geodesics. So that means I can cut my surface along each geodesic, and I will get some cut up thing. I'll get some cut up, maybe disconnected surface. When I talk about the topological type of my original geodesic or my original multicurve, what I just mean is the topological type of this cut up surface I get. Okay. So just as a quick example, you can imagine your multicurve is just a single geodesic. Okay. So a simple geodesic can do one of 2 things. It can be separating, which means that if I cut along it, I don't disconnect the surface, I don't break it up. And the second thing it can do is if I cut along it, then it can separate the surface into 2 surfaces, one of genus G and the other of genus, G prime, the other of genus G minus G prime, or some G prime between, say, 1 and G over 2, which means that I have 1 plus G over 2 different types of topological multicurves, topological types for a single simple geodesic. But now I want to talk about, if I have some weighted combination of them. Okay, so we're interested in basically understanding random multicurves. So in the case of genus 2, it goes back to the thesis of Mirzakhani that if you take a typical genus 2 hyperbolic surface, then the probability that a random geodesic is separated is 1 over 49. So I mean, she basically pinned down the topological type of a random geodesic in the case of genus 2. And what I want to basically be doing is taking the genus to infinity.
Sorry, what was random geodesic then?
I'll explain that in a second. So yeah, I owe you that definition. So I'm once again going to sort of I'm going to bring it down to a finite family and then pick one at random. Okay, so 2 questions. The first is how many multicurves are there on a hyperbolic surface of large genus? And the second is what is the topological type of a random such multicurve? So I owe you the definition of what do I mean by random. And also, what do I mean by how many? Because up here, they're infinite, so I need to do some cutoff again. So I should emphasize that this talk is really related to the geometry of the geodesics and not the surface. There is a beautiful and very large literature on the geometry of random hyperbolic surfaces of large genus. But what I'm actually interested in is I take a hyperbolic surface of large genus and ask myself, how does a random multicurve or a random curve behave on it? Okay. So now, as I said before, I owe you the definition of what I mean by random multicurve. So let me go ahead and explain that. So let's fix some typical, I fixed some, say generic hyperbolic surface X of genus G with n cuffs. The answers will actually turn out not to depend on X. Through sort of ergodicity arguments. Anyway, so I'll let this MC sub L of Gn, which a priori it depends on X, but as I mentioned just now, none of the answers really will. So it's going to be the set of multicurves on X of total length at most L. So when I talk about the length of a multicurve, remember that a multicurve is a weighted sum of simple geodesics. And all I do is I just sum, if my multicurve is gamma is equal to the sum of mi gamma I, then the length of gamma is equal to the sum of mi times the length of gamma I. So I'm imposing that that's at most L. Okay. So now I fix some topological type alpha, which is indexing to me the topology of the surface that I get by cutting X along this multicurve. I just call that alpha, and I let this MCL of alpha denote the set of all multicurves with that topological type. So this is just a refinement by topological.
Could you explain when you take a multicurve, you got these parameters. I understand what you do when you take a single geodesic or a couple.
Yeah, so the parameters don't affect
m times that.
The m does not affect the multi-type. Okay. That does not affect the topological type.
So you're not completing these delaminations.
Sorry?
You're not completing these delaminations.
So I couldn't hear what you said.
You're not completing these delaminations.
No, I'm not.
No, oh, okay.
No. Okay. So these are my MCL. Okay, so now I need to do a similar thing as I did before in the context of flat surfaces. I first let capital L tend to infinity so that I have a random G. I know what I mean now when I talk about a random geodesic. And the second thing I need to do is send G to infinity. So now I have the first statement is the analog basically of the statement that I had a few slides ago, which is that as L tends to infinity for very large L, the size of this MCLGN is L to the same exponent 2G plus n minus 6 times some constant BGN. And she showed that this BGN is both finite and positive. And it's basically the expected volume of the Thurston ball. Is one interpretation for it.
My memory is that a thing depended on the hyperbolic, there was a constant depending on the hyperbolic metric that you chose at the beginning there. That maybe later it was shown not to depend.
No, it's there is some formulation of this. So this BGN is the X.
Paper is BGN of X.
Yeah, so this BGN is the integral of BGN of X over all X. Okay. Yeah.
But
so there is a BGN of X, but that's not the thing that appears in this formula.
Are you integrating it?
Yeah. So this the formula that you get from this is the integral of this over all X. Yeah. Okay, so more generally, actually, the more general statement is that the number of multicurves with a given topological type, so just sort of a refinement of the statement, is also given by L to the 6G plus 2n minus 6 times some constant Y alpha, where Y is some finite number. So basically, so you can talk about sort of this is sort of the contribution to this count that's coming from those multicurves with topological type alpha. Okay. So again, we're talking about computations. We want to kind of compute these things. So she also provided an algorithm to compute these Y alphas through intersection numbers of psi classes. I might get to that later on. Although I should mention again, it's of the same complexity as the other formulas. In fact, it turns out to almost be equivalent to one of the formulas, which is that it's going to be exponentially complicated in the genus, the complexity of the algorithm. Okay. So now there's a relationship between volumes and hyperbolic, volumes of these moduli spaces of flat surfaces and the hyperbolic geometry, which is that this volume, this vol of QGN, is actually equal to this BGN times a constant, times just some constant. Well, I guess they're both constants, so this is not a very valuable statement. But the constant here is explicit and factored, right? So it's an exact thing. I mean, people basically view these as the same objects up to some overall normalization. Okay, so again, this statement is due to Mirzakhani in the case when n is 0. For general n, it was established in the work of these 4 authors that I mentioned before. Another proof, so the original observation that these were the same for general n just actually came from literally computing both sides and as some terrible sum, and then they realized that these terrible sums on both this side and this side were exactly the same up to an overall constant. But then more sort of geometric dynamical arguments were introduced later on by Arana Herrera, who's here at the IS, and by Bonin Telkupovsky, both in 2019. So okay, as a corollary of the previous result I had, so I given you a large genus asymptotic for this volume. So you can, just by plugging it into this relation, you immediately get a large genus asymptotic for this BGN, or equivalently for the number of multicurves. Okay.
So you're proving this asymptotic separately and concluding it for these.
Yeah.
You're not using the hyperbolic geometry to prove your theorem.
Well, yeah. So I mean, so actually, these 2 formulas, as I mentioned, so I'm using sort of these formulas, okay, which are the same actually in both cases. So, but yeah, I kind of came across this, personally, I came across this through the flat side, and then I translated. But sort of the formulas are more or less the same on both ends. Yeah. Right. Okay. So now let me tell you. Okay. So I wanted to. I sell you a definition of what I mean by how does a random flat surface look. So all I did so far was tell you how to count them, but I should now explain to you sort of how to decompose them into geometric objects that I can think about geometrically, right? So okay. So let's pick some square-tiled surface X. And the horizontal foliation in it will decompose X into a bunch of maximal cylinders. So in this case, for this square-tiled surface over here, there are 4 of them, right? There are 4 cylinders I get. And each cylinder has a waist curve, which I call gamma I. So this gives rise to a multicurve, which I call gamma, which I just defined to be the sum of the height of the cylinder, Ci, times gamma I. So for example, here, I have one cylinder of height 2, so I have like 2 gamma 1. I have another cylinder of height 1, this gives me a gamma 2, another cylinder of height 1, which gives me a gamma 3, and another cylinder of height 2, which gives me 2 gamma 4. So it's the sum of all of those guys will give me a multicurve on my flat surface now.
So the heights are always integer.
Yeah, that's right, because I have a flat surface. I have a square-tiled surface. So I have a surface that's obtained by gluing together a bunch of squares.
Of the same size.
Yeah, exactly.
Okay.
Good. Yeah. Okay. Yeah, I mean, so if you want to kind of view this, you can kind of try to view this as a discretization of a general flat surface. You can scale down everything by root n or something like that. But yeah.
But the height function would be more like an exact one form rather than function is, because we can go up and appear to came from below, right?
What do you mean?
Like I could imagine that, for example, if I just take torus, what will happen there? The height function will be not a function, but
I mean, if you just have a square on and you glue the opposite sides, it's just gonna be the height of the square.
So I actually guess I don't quite understand why you can get away with unit squares. I mean, somehow in the description of this.
Oh, well, no, I mean, so if I want to talk about what I mean by a random square-tiled surface,
Okay.
a random square-tiled surface, yeah.
Yeah, because I mean, if you start with a description of of a hyperbolic manifold this way. It's not.
Yeah, no. So this is purely, first of all, on the flat side. Yeah, yeah. This is purely on the flat side right now. Yeah. Are there any, which turns out to be equivalent to the hyperbolic side, but not for this reason. Yeah. So yeah,
Okay.
yeah. This is not. I have not explained any sort of geometric explanation of why the two are the same. I just stuck to went back to the flat side and tried to explain to you what do I mean by the geometry of a random flat surface.
So it's equivalent to what did you say? I mean, this special case where you have these, you're gluing these squares.
Yeah.
But you're saying it's equivalent to something more general.
No, I was just mentioning, although it's not related to the slide, that I was just mentioning again that there's a relationship between the flat geometry and the hyperbolic geometry, this volume relation. It tells me that sort of the number of flat surfaces is almost equal to the number, up to some scaling, it's equal to the number of hyperbolic surfaces. But I want to tell you now what do I mean by how does a flat surface look? And that has nothing to do with the hyperbolic stuff. So I just wanted to make that clear. Are there any other questions before I keep going? Okay, so I've now cut out my flat surface, my square tile surface, into a bunch of cylinders. And what I can try to, I want to be able to sort of extract from it something I can view as geometric, so I can get a feeling for how these surfaces look, and I will encapsulate that in a graph gamma. Okay, so the vertices of gamma are given by the connected components of what I get by pinching all of these waist curves. So in particular, in this case, they're going to be, as you can see, 5 connected components by pinching or just cutting along these waist curves. The edges are going to be the waist curves themselves. And the unpaired, it will have some unpaired half edges, which you can view as basically the conical singularities at total angle pi, the poles of the quadratic differential. These will play a minor role in this talk. You can kind of assume that they're none of them, and you won't lose much. Yeah, so in this case, as I've just mentioned, you have 4 edges coming from these 4 cylinders, and you have 5 vertices coming from the fact that there are 5 connected components you get by cutting along them. So the topological type of this multicurve, this multicurve, so multicurve now associated with the flat surface, is basically just fixed and is fixed by the same thing as this graph. So this graph will tell me everything about the topology of, or will tell me about the topology of this surface, basically.
Maybe you said this, but is there some choice in defining this decomposition?
Well, I
could start somewhere and then take the foliation from that point to the left, say. Like, how do you choose your endpoints in this picture?
Yeah, I mean,
is there something independent of that choice that comes out at the end? Or?
Yeah.
Okay.
Yeah.
But I mean, poles of the quadratic differential should be important.
Yeah.
I don't quite understand what you say you could ignore it.
Well, I can assume that as I mentioned.
Not very many is the point.
Yeah.
Okay,
Yeah.
not very many.
Yeah. You can, if you want, my theorems all apply when n is 0.
Yeah.
And yes, that's all I meant. Of course, the poles will affect the geometry rather substantially. But I'm just saying that if the poles bother you, which I guess they don't, is you can just imagine that all my theorems just restrict to those quadratic differentials that don't have any poles. But if you like the poles, by all means, feel free to think about them. Yeah. So okay. So right. So now again, we're on the flat side. So I'll let this Sn of upper gamma of Gn denote the set of surfaces, the set of square tile surfaces in this Sngn, who's associated with this graph gamma. And the theorem is that this, after I scale appropriately, I always have to scale by this, n to the 6g plus 2n minus 6, that the number of such surfaces after the scaling exists. And they also provided formulas for this number in terms of intersection numbers of certain algebraic geometric classes. And in particular, if I take this z and I sum over all gammas, I get back the volume, right? I'm just summing over all possible topological types. So I mean, I'll give you an example of what such a formula looks like. I kept on telling you it's complicated, but maybe I should just give you an example and you can now agree or disagree with me that it's complicated. So let me just take g equal to 2, okay? And if you plug in this formula, this is what you'll get, okay? These bracket tals, these are certain algebraic geometric invariants. They're intersection numbers of psi classes on the moduli space of stable curves. I might get into that a little bit later. Okay, so right, so this gives one a formula, although a fairly complicated one, and one that sort of involves various algebro-geometric information for these volumes. Okay. So I should just quickly mention that there's a generalized relation. I mentioned the relation on the level of volumes, this relation between the volume of the space of the total number of flat surfaces and the total number of multicurves. But you can sort of refine this by topological type in a sense. So if I fix some topological type gamma or alpha, again, you can associate it with some graph gamma, and you have this relation that tells you that the number of flat surfaces with graph gamma is up to the scaling of kappa, this explicit factor, this explicit thing times the number of multicurves with topological type alpha. So you can go back and forth with them on the level of statistics. So this basically implies that statistics of random square-tiled surfaces and of hyperbolic multicurves coincide. So I'm gonna for most of this talk, I'll mainly live on the square-tiled surface side, on the flat side, but you can kind of translate back and forth between them. As I mentioned before, this is originally sort of just realized on the level of exact coincidence of formulas with more geometric proofs are found later on. Okay, so back to this theorem. So as I mentioned before, we know that as n tends to, we have some, the theorem tells you some sort of large genus asymptotic for how big this volume is as g tends to infinity and as n stays fixed. And we have a formula for this volume in terms of intersection number. So I have two kind of tasks to do. I have to first, if you imagine trying to prove this theorem, what you would have to do is you have to first understand the asymptotics of these intersection numbers. After all, my formula that I'm eventually going to analyze is in terms of some algebra geometric invariance. I have to be able to take limits of those objects. And the second thing I have to do is be able to plug them into the formula and see what I get, which is not as easy as it sounds because the formula itself, going back here, this is just what you get for g equals 2. In general, you get some total disaster, which is a sum of exponentially many graphs. Okay, so so let me table the first issue for now. I will, if I have time later on, I'll try to mention it. But for now, let me mention on the second issue. What you do is you have this formula, which is a sum over a bunch of stable graphs, which is a sum over all these graphs gamma. And you analyze the contribution of the sum depending on the type of graph you get. So the statement, which you can imagine simplifying things a lot, is that if your graph gamma has 2 vertices, then the total contribution of that is little o of this asymptotic. And if a graph has 1 vertex, then it's basically the total contribution of all graphs with 1 vertex is giving you the whole thing. So this is really the simplifying feature that allows you to compute. And of course, the difficulty is in the first point, right? I have exponentially many graphs which have more than 1 vertex. I have to somehow say that they don't contribute very much. Okay.
So the dominant one will obviously be the 1 vertex graph.
Yeah. Although 1 vertex graph, I should also mention, is not totally, there's a bunch of, there's probably like log g of those. And in order, so that's not too many, but actually to get to you get some sort of sum over log g, which is tending to infinity like many things. And this remarkably turns out to be computable. It's not obvious. But yeah, I would definitely say that the bulk of the difficulties is in task 1. Okay. Okay. So so if you sort of read this for a moment, what you'll immediately realize is what this means is that with probability basically 1 minus L1, this gamma graph that I had before has just 1 vertex. Okay, so in terms of what that means in terms of the geometry of a surface, if I sort of look at the horizontal foliation and I pinch along all these waist curves, I get something connected. So if I pinch along all my waist curves, I don't disconnect the surface. In terms of hyperbolic geometry, what that means is that if I take a random multicurve on my hyperbolic surface and I cut along it, then my surface still remains connected. So this is one of many testaments to the fact that large genus surfaces and hyperbolic geometry are extremely well connected. If I take like a random geodesic, even one that has many edges, many components, it will leave the surface connected. Okay, so I have a little bit on the single vertex graph.
Sorry.
Yes.
I'm sure this is just that I'm missing the whole point, but you're only talking about the horizontal geodesics.
Yeah.
I mean, there might be, there are others.
Well,
or at least it seems to me there are.
Okay, right. So maybe so you're talking about the flat picture, right?
Yeah.
The flat picture, yes.
Well, I mean, I'm talking about both pictures, but I mean, you know, I don't have too much trouble translating. So
yeah. So on the first of all, on the hyperbolic side, I'm not restricting at all to any sort of horizontal geodesics or anything like that. On the flat side, yes, you're right. I am sort of making a somewhat arbitrary choice about restricting to flat sort of cylinders.
Right.
But there is a procedure that allows you to sort of cook up the surface just from that information. Like reconstruct the surface. If I know, for example,
out of that, or out of those flat geodesics, yeah.
Yeah. So if I know basically the structure of this graph and the lengths, the heights of these things, then I can sort of get the surface back.
Right, but that still means that it's only those geodesics that you're cutting.
Right. Well, my goal is not necessarily to compute geodesics. My goal is not necessarily to understand geodesics on the flat surface. It's to just understand what the flat surface, get some sort of geometric understanding of the flat surface. So I guess, yeah, so maybe I should have made this more.
Sorry, that's clear to me when you say it that way.
Yeah, okay. Yeah, was there a question on your end? Are there any other questions before I keep going? Yeah. So yeah, again, on the flat side, I'm trying to understand the geometry of the surface. What that maps to on the hyperbolic side is understanding the geometry of the geodesics. So yeah. Right.
Okay. You keep on jumping between the two just to illustrate, not because you use it.
No, absolutely. Yeah, again, it depends on your favorite perspective. I'm doing it for the person.
Yeah, I like the other one, but
yeah, I know that. The issue is I think about the first one usually. So yeah. Okay, so right. Okay. Where was I? I was here. Okay. Right. So I told you now about the two vertex graphs. It's quite a lot of work to show that they don't actually contribute asymptotically. But let me now just take that for granted and talk about the single vertex graphs, which are the ones which are constituting the majority of the space, right? So I remind you that I'm taking sort of random square tiled surfaces, S in this SNG, it's SNGN. I'm first letting n tend to infinity and then letting g tend to infinity. And as I mentioned before, this underlying graph has one vertex with probability 1 minus the law of 1. So it turns out that so there are actually g plus 1 such graphs. These graphs can have multi-edges, is the reason. So these graphs are all of this form gamma GE, where it's a single vertex, but it has E edges connecting it to itself. Okay. So what that means is that my square tiled surface has E cylinders. It has E cylinders, or in terms of hyperbolic geometry, my multicurve is composed of E simple geodesics. Okay, so this proposition over here tells you how to compute the probability. As I said before, with high probability, my graph gamma is one of these gamma GZs. So what's the probability of seeing a given E? It's given by this explicit formula. So it's given by the so maybe you should be looking at the subject over here. It's given by the ZE over some something factored, and the ZE is like a somewhat complicated sum. It's like some sort of multi zeta series in a sense. Some sort of combination between a multiple harmonic series and a multiple zeta series. So
what's that mod A equals M? What's mod A?
Oh, mod A is the sum of all the A's. Yeah. Okay. So this is what I meant when it said even the single vertex graphs is not entirely trivial. You have to actually sum all of this. You have to be able to compute the sum over all E of this, which turns out to have a nice form. Okay, so
so you're going to use that zeta M goes to 1 rather quickly when M goes to infinity.
Yeah, no. If you use that, you get the wrong answer. You don't get the right answer if you use it. You actually So it's a combinatorial game of generating series really is what's underlying. Yeah. Okay. So how much time do I have left? Is it 15 minutes?
Yeah.
Okay. Okay. So let me mention a few statistical consequences of this. So I mentioned one of them, which was that my graph E.
Sorry, go back.
Yeah.
You're using that to see the series. Now M is fixed. That's a finite sum.
Yeah, so this thing is just a number. And now the statement is the probability that my graph has E edges. It's given by basically the Z sub E of 3G up to some factors.
Okay, but when you let G go to infinity, you will be letting M go to infinity. And when you let M go to infinity, we'll be having zetas large.
Yeah, but there will be a few of them there. This is a sum over all of them. So you're right that maybe a lot of them will be one. But a few of them will just be like one or two. And those actually one or two does affect, it affects that constant 4 over pi in front.
Okay, so far you haven't studied. So far you claim, wait, this is a proposition that is based on the fact that the guys with two, you've removed.
Yeah, so I've removed also, so yeah, this is basically telling me the probability that I have that my graph is given by this specific guy. Yeah. So, okay. Any other questions? Okay, so let me mention a few statistical consequences of this. So I give you one, which is kind of the probability of seeing a given graph. From this, you can start to fish out various other, from this, and you actually need quite a bit more work, which was done by these 4 authors. You can fish out a number of other geometric consequences of this problem of these formulas. So the first is that this E, the number of edges in my graph, which is again the number of cylinders in the flat surface side, or the number of geodesics in the multicurve side, is given by a Poisson random variable with a fairly explicit Poisson parameter. Okay, so what that basically means on the square tiled side is that I have about log G over 2 cylinders on average. And on the square tiled on the hyperbolic side, that means that my random multicurve has about log G over 2 geodesics. So as you can see, this is sort of slowly diverging, a slowly diverging number of either cylinders or geodesics. And the fact that I have one vertex at the end of the day means that after I pinch, cut along these diverging number of geodesics, my surface remains connected. Okay. Another sort of curious fact is that the law of E, I said it was a Poisson random variable, but you can actually sort of get computed up to like a higher order expansion. And you'll see that it's very, very close to the number of cycles in a random permutation, where that random permutation is sampled under something called an Ewens measure, which basically means that you weight cycles of length k by 1/2 times zeta to the 2k. Okay, so there are other consequences that you can get from this. I've already talked about the topological types of the structure of the graph, but you can actually also say something about the M's, right, or the heights of the cylinders. So on the square tiled side, you can say, for example, the probability that all cylinders have height at most a is basically equal to the square root of a over a plus 1. And on the hyperbolic side, the probability that all the M's are at most a is again the square root of a over a plus 1. So particularly the probability that all cylinders are just 1 unit tall, or the probability that your geodesic is, on the hyperbolic side, the probability that your geodesic is so-called primitive, or sorry, your multicurve is primitive, which means that all gamma are 1, is equal to square root 2 over 2. Okay, so there are also others that I'm not listing. You can talk about large deviations. I mean, there's a wide slew of sort of statistical consequences you can fish out from these formulas. Okay, so I want to mention the number a quarter somewhere in the talk. So I'm going to talk about now how you can use these results to count various structures in flat surfaces. Okay, and so now at this point, I'm not going to go back and forth between flat and hyperbolic. I'm actually going to just stick to flat. Okay, so as I mentioned before, any flat surface has some conical singularities, which are vertices at which the total angle is not equal to 2 pi. So equal to some either multiple of 2 pi or just pi. And these are also known as saddles, and they correspond to zeros or poles of omega, as I said before. So a saddle connection is a geodesic that connects 2 saddles. So an example is over here. These 2 saddles are actually, so it connects this red thing would mount to a saddle connection. And a maximal cylinder is an isometrically embedded cylinder whose boundaries are unions of saddle connections. So for example, this green rectangle on the octagon, after I fold it up, it will correspond to some cylinder on the flat surface. So what I want to kind of do is I want to count these objects. let me count cylinders, for example. So let's fix some quadratic differential xq and some real number L. So I'll define this weighted cylinder count. So n of area of Lx is equal to the sum of the area of C, where I'm summing over all cylinders, over all maximal cylinders, whose circumferences are most L. So you can, so an A of S is the area of S. So I'm kind of summing over all cylinders whose circumferences are most L, and I'm weighting them by area. And you can kind of interpret n area of L as counting the number of closed geodesics, but they're uncountable in many of those. So what you're really doing is you're fixing a closed geodesic and thickening up into a cylinder, and then I'm counting like that. So you can, so I'm going to view this as sort of a weighted counting of closed geodesics almost.
There's not billions.
Sorry?
These are flat billions. This is exactly the cylinders are flat billions.
Yeah. These cylinders very much come up.
I'm just emphasizing you in the flat case.
Yeah. So let me not use the word hyperbolic after this. Yeah. Okay. So so it's a theorem that goes back to Eskin and Mazur back in 2003 that for almost every xq, so if you kind of think a typical xq in the C, C should be actually, sorry, the any quadratic differential, almost any quadratic differential, then the C area defined by this n area, this number here, divided by pi L squared, this limit exists, and it actually doesn't depend on your choice of xq, as long as your choice is generic in a sense. So the surface is, so this count really is
one of the big unsolved problems, that you have the subset of those billions, which is not.
No, this is
which you don't know.
Yeah, that's of course a very deep question, which I'm not going to address in this talk. Yeah, right. But I'm talking about, say,
that's almost every.
Yeah, I am a probabilist, so I talk about almost every. Yeah. So right. So this limit is called an area Siegel-Veitch constant, and what people are often interested in is computing it. Actually, this Siegel-Veitch constant contains a rather some geometric information, which I will not go into much more. But okay, so the point is that you can compute these constants in terms of volumes. So you can write volumes. Sorry, you can write these areas in terms of these volumes of the moduli spaces that I had in the previous slide. So in principle, if I had the volumes, I can actually compute the C area. So okay, you can go ahead and do that. And what you'll get from the previous theorem that I mentioned before is that as G tends to infinity, you can show that this area Siegel-Veitch constant is a quarter. Okay, so now a quarter probably makes people's eyebrows raise, because they know that a quarter is related to lambda 1. Yeah, lambda 1 in hyperbolic geometry. So you can ask if there's a connection between the two, and I actually can't give you a definitive answer either way on that. I'd been told that there might be, but I wasn't told what it was. So that's a very disappointing answer, I'm afraid. But I don't know one way or another whether or not this 1/4 is related to the largest eigenvalue that you see on a hyperbolic surface. So, but I thought I would mention it nonetheless. Okay, so I have 5 minutes left. So I just want to conclude by mentioning a little bit about the intersection numbers in the large genus asymptotics, and then I'll close. So I'll give you 2 definitions. So as I mentioned before, these volumes are written in terms of these algebraic geometric invariants called intersection numbers. I'll give you 2 definitions of these intersection numbers. The first is an algebraic geometric one on this slide, and the next one will be a combinatorial one in terms of graphs. Okay, so if you don't like one, if you don't like this one, just wait a slide. Okay, so so just to quickly go through this one, let's let MGN denote the moduli space of smooth genus G curves with n marked points. We'll let MGN bar denote its compactification. So this is the set of tuples C, x1, x2, all the way to xn, where C is a stable curve of genus G, and x1, x2, all the way to xn are a collection of non-singular points, non-singular points on it. Well, Li be the line bundle on this moduli space, whose phi over this point is given by the cotangent bundle on that point, and we'll let psi I denote the first term class associated with this Li. So for any n tuple D, which is D1, D2 all the way to Dn, we'll define this intersection number, tau of D1, D2 all the way to Dn. This has the physics notation of correlation functions. And indeed, this is sort of the original reason why Witten introduced them in the first, Witten popularized them or introduced really this notation in the first place, which is given by the integral over the moduli space of this product of psi I to the Di. So this is going to be non-zero if the sum of the D's is 3G plus n minus 3. And these are ubiquitous objects in mathematics. In mathematical physics, they appear in correlation functions. for quantum gravity models. This is why Witten originally was interested in it back some 30 years ago. In algebraic geometry, these are fundamental invariants that you see. Intersection theory and dynamics and geometric topology, which is the focus of this talk. These are things that you need in order to compute these moduli space volumes. You know, that complicated formula for Q20 may exactly involve these numbers. Okay, so now let me give you maybe a more geometric or maybe a more combinatorial definition of these intersection numbers. So to do that, I'll define a ribbon graph, which is a graph possibly with loops that have a cyclic ordering at each edge. So by cyclic ordering, I just mean that you take all the vertices, the edges around a point, and you define some cyclic ordering around it. Then you thicken imagine you thicken each edge into a thin rectangle or a ribbon, and that gives rise to a surface with boundaries. So I take this vertex here, and I just kind of just thicken each edge into a little ribbon, and I'll get something that looks like this. And if I do that for a graph, I'll get something. If I do something for a graph, maybe one of the simplest ones, just having 2 vertices and 3 edges, I'll get a surface that looks like this. So I'll let RGN denote the set of ribbons with the following 3 properties. The first is that it's trivalent, meaning that each vertex is of degree 3. And the second is that the resulting surface, this ribbon surface, has genus G with n boundary components. Okay, and a metric ribbon graph is a ribbon graph with a length associated with each edge. So that gives me a notion of a length to each boundary, and I call it integral if every edge has an integer length. Okay, so this proposition back, I guess it was due to Kontsevich back some 30 years ago, is another interpretation of how you can define an intersection number. So it will define you a generating series for this intersection numbers, which will allow you to fish them out. Okay, so I'll let NR of B1, B2, all to Bn denote the number of metric ribbon graphs with the following properties. So this R, so the ribbon graph has sort of, the underlying ribbon graph is R, and the lengths of its n boundary components are B1, B2, all the way to Bn. Okay, so I can look at the sum now, which is some weighted sum. So I sum over all trivalent ribbon graphs with integer edges. It's typical to divide out by the number of automorphisms. And the claim is that this is a polynomial in the B's of degree 6g plus 2, 1 minus 6. And the top degree part is given by a polynomial whose coefficients are exactly the intersection number. So this kind of gives you a way to algorithmically compute them if you like. If you're able to actually compute this number, this thing, then you can compute the intersection numbers. So you can interpret this as a combinatorial. If you didn't like my algebraic geometric definition, you can also use this as a combinatorial definition for these intersection numbers. Okay, so there are various ways to compute these things. You can compute them through certain recursions, which are basically related to the Virasoro constraints of the so-called Witten's conjecture. It was proved originally by Kontsevich after Witten conjectured it in 1992 and 1991. And then there have been a bunch of alternative proofs since then. This is not a very complete list. You can also compute various generating series for these intersection numbers. Again, a somewhat incomplete list is shown over here. I'm giving you a formula for what this recursion looks like. As you can see, it's somewhat, I don't necessarily expect you to focus on it.
Why are they called Virasoro? What's that have to do with Virasoro?
Yeah, so you can couple up a generating series for these intersection numbers, and then this constraint, this recursion here, is what you get by acting on a differential operator on that generating series. And the differential operator is something that comes from the Virasoro algebra.
Okay.
Yeah. Okay. So I want to
There's an integrable system.
Yeah. There's it's KDV that underlies. KDV.
So that's where it comes from then?
Yeah, correct. Yeah.
I mean, this came from, I think I was talking to Steve the other day, right? You know the history better than anybody. This came from Itzik and Zubair. It came from the combinatorics. Then Witten made the conjecture.
Yeah, that's right. Yeah,
it came from the combinatorics.
Yeah, well, I mean, also these intersection numbers were introduced even earlier back then.
Migdal.
Yeah. Okay, so I just want to quickly state a theorem on. Okay, so before I say that, I'm going to state the question, which is that these intersection numbers, this picture is total overkill. I agree. Either you can't see it, in which case it's useless. Either you can, in which case it's a little too much. But
that's a rational numbers.
Yeah, these are rational numbers indeed. But as you can see, at the moment G is large, these things become fairly complicated. Already at genus 30, this is some 20 over 30 digit number. But I need to be able to compute them if I want to compute the volume. So the basic question is, do these numbers have some sort of tractive asymptotics as the G tends to infinity? And the statement is that indeed they do. This tau, if I imagine that my D is D1, D2 all the way to Dn, and these d's have to sum to 3g plus n minus 3. This tau d1, d2, all the way to dn is given asymptotically as g tends to infinity, as long as n is not growing too quickly. So you need the n to be equal to like little o root g. It's some factorial over a product of factorials. So it's a fairly explicit object. So in particular, if I sort of normalize out by this guy, it's equal to 1 in a sense, which, okay.
You're not suggesting you can compute those rational numbers by knowing the size of the numerator and the denominator and get it from the asymptotics.
Well, there's no way I'm going to compute the numerator.
I was just trying to understand. You're just computing an asymptotic.
Yeah, that's right. Yeah. I don't think I have no idea how you.
The reason I say that, it's not just a joke. If you say the partition function,
yeah,
you can write down an asymptotics and it's an integer, and that asymptotic is so good that you can write down the integer from the asymptotics much more quickly than any other way. So there are sometimes asymptotics.
Yeah, there are certain situations which you can do that, but that's not the relevant.
That's a rational number. I don't think so.
Yeah. So okay, I'll just take 2 more minutes. Sorry. Which is that the first is that you can view this as a kind of universality statement, which is that if I normalize out by the answer, then my result is always equal to 1. Okay, that kind of sounds stupid because what I'm saying is that if I multiply this thing, if I move that over to the other side, I get something that does not depend on my d. Now you can say, okay, well, you just took the d-dependent part and moved it over to the side. So why is that a useful statement? This is actually a very conventional, this is a fairly standard normalization of these intersection numbers. So if you sort of take a fairly standard normalization of the intersection numbers, then you get something that's independent of the d asymptotically. So now the statement I should make is that this is predicted by this pair of 4 authors back in 2019. And it was kind of surprising when they predicted it because no one believed that these intersection numbers would have any sort of tractable asymptotics. And the third is that I want to make the statement that this theorem is false if I drop this assumption. So if n is scaling like square root of g, then this intersection number can have different asymptotics from this. And another proof of this result. In this case, when n is log g appears somewhat recently. Okay, so I'll just skip to the end, which is a quick summary. So I looked at asymptotics of the geometry of random square tiled surfaces, or of multicurves, or geodesics on hyperbolic surfaces. There was an enumerative aspect to the talk, which is counting the total number of such surfaces, which is closely related to volumes and moduli spaces. And there's a sort of statistical side to it, which is on understanding the geometry of a randomly chosen object. And you can summarize the geometry through a graph. And in computing the volume, you actually kind of get along the way information about statistics of these graph counts. And the proofs are based on an asymptotics of these intersection numbers. And I didn't get the chance to show these arguments, but actually the way in which you analyze these intersection numbers is by throwing a little bit of probability into the game. You can interpret these recursions, these neurosort constraints probabilistically, and that will help you to analyze them. So thanks again, and I apologize for going over.
So there's some further questions or comments?
So this proof, the very last sentence, you proved it using probabilistic. So you take the intersection numbers, what kind of probabilistic?
Well, so it's coming from the recursion. So this recursion, so the proof is kind of based on a probabilistic interpretation of this recursion. So, so what you do is I can very quickly say, so schematically, the interpretation, the recursion looks like this, okay? Okay, so the last term is irrelevant, okay? The first term is kind of good, and the second term is kind of bad in a sense. By good, I mean that, okay, so what you really want to do is you want to decrease this n down to 1, because I know what this intersection looks like in the case when I only have one of these d's. Okay, I can compute it explicitly in that case, and I can also compute it explicitly if I have 2 d's. The problem is if I have like 20 d's and I'm going to have like a page, if I put it into Maple, I'm going to have like a page of, like a huge page is the formula is going to be like a page long. So I want to be able to decrease the n here. Okay, so the first term decreases the n, but the second term increases it. So I have a fight between increasing and decreasing. So our priori hope is that, okay, if I forget about the red term, then maybe I can do something. Okay, you can, that's indeed correct, but if you drop the red term, you get the wrong answer. So what you actually have to do is kind of view this as a random walk, like, you kind of with some probability, you decrease n, with some probability, you increase n. And by analyzing the random walk and kind of what's that's doing to the intersection number, you can be able to pinpoint asymptotics.
Where's the random walk
The random walk, you can kind of view it as like, I with some probability, I start expanding.
But is it on the, what is it on?
It's on the n space, so z, there's z.
Just Z.
There's z, yeah. So you're actually taking, it's just z.
And the
Yeah.
number 3/8 or whatever it was, what's the number in the exponent? Something to the G. Is that an eigenvalue of the, is that some, where's your main asymptotics? They 8/3, not 3/8.
8/3. I don't know of any sort of eigenvalue or Lyapunov interpretation of the subject.
How did it come out from your analysis?
Remarkably, I mean, so I have a computational. I don't have a good answer to that question. Yeah. I mean, you're multiplying by powers of 2 and 3 all over. 6 is such a.
Okay, 3 and 2.
Yeah, 3 and 2.
So is the key point the analysis of these asymptotic analysis of these intersection numbers?
So I would say it's twofold. So the first is that you indeed need to analyze these intersection numbers, which I view as like the main one main component. The second component is actually plugging it in. I mean, this actually in terms of length, showing that the number of graphs with 2 vertices don't contribute was also longer probably than the intersection number proof. So yeah, those were probably the two most involved points of the work. Yeah, please.
Let me just make a comment that there's a very efficient way to get these asymptotics of intersection numbers and volumes using a physics style argument. As you know, there's a generating function for these numbers involving a matrix integral.
Right.
Okay, and whenever you have an integral representation, you can find large order behavior of expansion in a parameter by looking for an auxiliary saddle point to that integral.
Yeah.
Okay, and in these matrix integrals, you're integrating over eigenvalues.
Yeah.
The asymptotics come from moving one eigenvalue from its dominant saddle point to another saddle point.
Right, yeah.
And that gives you in a few lines these asymptotics, all the known asymptotics, let's say for the Weil-Petersen volumes.
Yeah, so So I know that in the Weil-Petersen situation, people have these remarkable works that, I mean, I guess if you have these JT matrix, I mean, the models for JT gravity could spit out these.
It's true for the intersection numbers too. It's just a different matrix.
Well, I didn't know about the intersection numbers. So
you can take the intersection numbers. Actually, you can take as a limit of volumes when you take the boundary volumes to large numbers.
Yeah, that's right. Yeah.
So you can see it.
I see.
So all of that stuff. Now I don't know how to establish it rigorously.
But then I'm curious to know if this phenomenon that I'm describing here, the sort of universality phenomenon, in a sense that you have this very weak dependence on the D's. Does that have a matrix interpretation for you?
It probably does, but I don't know what it is.
Okay.
So are these the cubic matrices that?
Well, that would be one way. There are several different matrix representations. The easier one is the so-called double-scaled. Where you look at the edge of the semicircle distribution. This is a way that Kunkov.
Yeah, that's right.
Studied it.
Yeah.
But it's so in any event, it's a very efficient way to produce it. You can get asymptotics that are in all these different regimes of taking things of order G over G and
right. Yeah. So I should. So this is definitely a very interesting route. And the only thing I can comment on, I mean, my only experience with these objects is that I tried to fish out this asymptotic from the area matrix.
Right. That's the one.
And I somehow couldn't see an easy way to do it, but that's probably my mistake.
I would be very surprised if there wasn't a way to do that.
Yeah, there might be. At least heuristically.
Area matrix is purely oscillatory, is it? Or is it not?
Well, it's more like the edge of GUE or something like that.
So Tracy Woodham edge.
Yeah, Tracy Woodham edge. Yeah. Yeah. So somehow this theorem should be, at least heuristically on a physical level, contained in there. I couldn't quite see the origin of it, but that was probably my inability rather than the truth of it. Yeah. Although I have little doubt that, I mean, there will be some matrix model for which you would be able to at least heuristically see a theorem.
Yeah, and this number like this 1/24 to the G.
Yeah.
That basically is the value of the thing in the Boltzmann weight at this auxiliary saddle point.
Yeah, 1/24 to
an instant on action. It's you can compute that like in 2 lines.
Yeah, the 1/24 to the G I was kind of seeing, but the rest of the, yeah, anyway. Yeah.
Well,
I'm sure that there is a way. I'm not saying that there isn't. Yeah.
The 6G double factorial, that's 3G factorial over G factorial. That's 2G factorial roughly for fixed n. That 2G factorial comes from the fact that it's one eigenvalue out of many moving. Things like that. So a lot of the structure comes right away.
Yeah, but it's, I mean, my experience from years
yes,
when people were doing sort of universality calculations your way with saddle points, it was the number of variables is growing, so it's very hard to make rigorous.
That I can believe.
But of course, the saddle point giving the answer is always very pleased.
Yeah.
And you would say to me, it just comes out. If he's like,
Okay, well, thanks again.